Good morning. I am happy to see a good crowd of people joining us for uh, this morning's webinar, which is on accidental and incidental polarization effects. Basically, the effects that we don't necessarily want but need to understand to design systems. And I am John Herlocker, a principal optical scientist at Breault, as well as a member of staff for technical support. I do a little of everything here, and this is one of the things that I love to do. So what I'm talking about when I describe accidental and incidental effects are not the things that we do intentionally with polarization or to polarization, using devices that you may be familiar with, like polarizers, wave plates, polarization selective coating, or something else. Things made out of crystals, things made out of anisotropic materials, wire grids, and so on. Sometimes we get polarization effects that we don't really intend, where none of these quote polarization devices, these devices with designed polarization properties, are present. The polarization changes anyway, somehow. And that's because all optics are polarization devices to some extent. And really, all of you who have had a physics course know this already. It's just that we often don't realize the extent of it. And we need to be conscious of this when we're designing systems. So the way I'm going to try to help you be conscious of this is by talking about a few simple systems, and I'll show you examples of some of the things that go wrong in the simplest of systems. And we'll talk just a little about what happens when things get more complicated. But more complex systems are a subject for hours or days of discussion, so we won't go too deep. So don't be afraid that it's going to be too deep. It's going to be fun. So a simple imaging system, one of the simplest imaging systems that gives a really dramatic result that I like to talk about, is an Amichi prism followed by a lens. So basically what's happening here is we're completely filling one input face of the Amichi prism with linearly polarized light. And in our perspective, this is kind of horizontal. I haven't shown you the coordinate system, but I believe this is the x-axis in our system. We'll look at it live in ASAP in a couple of minutes, and I'll and I can confirm that. But we basically have a reflecting roof on the backside, and then we exit at a right angle to our input. And then we go through a lens to a detector. And one of the really dramatic things about this is amazing things happen to polarization, but if you didn't even pay attention to the polarization settings, there's still something very dramatic that happens in just the imaging characteristics of this. So you might expect the Airy function. This is basically a square root of irradiance function at the detector. And if we ignored polarization, we would get this. We'd get a nice Airy function. But with the given polarization here, we actually see this, a pattern which clearly no longer has full radial symmetry, and which has essentially two mirror planes, one here and one here, describing its behavior. So clearly reminiscent of an Airy pattern, but an Airy pattern having a bad day. And so this is not necessarily what we want. If we're depending on imaging characteristics that the classical Airy pattern would describe, we're not necessarily going to get quite what we want in a system with polarization. And to take this just a little further, looking at the light after the Amichi prism, we see this pattern. We now have elliptically polarized light, and because of the way the upper half is flipped from the top to bottom, the lower half is flipped from bottom to top as we go through, we see a line of symmetry in the pattern right through the middle, and we have elliptical polarization. So not only do we see the symmetry of the reflection, but we have some ellipticity here, whereas we started with linear and horizontal polarization. We've come out of that orientation and developed a little bit of ellipticity. If we go on through the lens and we look at the polarization at the image plane, that is also pretty intriguing. And you can see to some extent why we might get these planes of symmetry in the PSF, the point spread function. There's certainly some kind of symmetry about this center. We're almost linear on axis, and very nearly perfectly horizontal. There's just a little bit of rotation there. And then we get basically, we approach circular at some point. We actually are seeing the ellipse in effect rotate as we go in this direction. So the polarization at the image plane is very entertaining if you like that sort of thing. And now I want to go to ASAP Live just to prove to you that I didn't just draw these things for fun, that they come out of a real system. So this is the system in ASAP, and this is the PSF if I ignore polarization, which I can do in the same model, by the way. I do not have to create a model with unpolarized light. I can simply say ignore polarization. This is the same model with polarization considered in the final result. This is that crazy resultant polarization at the image plane. By the way, the scale of this is not quite the scale of this. This has a full scale plus or minus about 15 microns. This has full scale plus or minus about half that. So I'm only really looking at the polarization in the center half of this figure, in this polarization figure. But it gets weaker as we go out so that we can't see the shapes as well. One thing to remind you of if you are familiar with ASAP, or to tell you if you're not, is that the size of each sort of unit cell in this pattern, the size of the figure representing the polarization is proportional to the energy, well, actually the field in that, well, in this case, it is energy, actually. It's proportional to the energy in that cell of the pattern. So as it gets smaller, that means there's less energy there. And that's useful to know, and you're going to see that again later. So there are no quizzes, but that's something you want to pay attention to. So just to prove to you that we're really doing something here, I'm going to go to the detector, and then I'm just going to zoom in manually. I could do it automatically, but this is more fun. You see the classic Airy pattern here, and this is actually log Airy pattern, or log of irradiance in this case. And you can then simply hide that one, and you see the polarized pattern. So I generated both of those patterns at the detector, backed them off the detector just a wee bit so that they would not clash with it. And now you can see the pattern. And I can always actually bring back the other one. So if you like to do side-by-side comparisons by just alternately doing hide view or hide visible in the 3D viewer, we can see these things. So this is a dramatic example, and I kind of wanted to lead off with that. So just to give you a little background on all of these files, this is something that will be available to you after the webinar. It's a project file that has all the files I've used to put together the presentation and a few extras, including even the chart template files, which I'll introduce you to in a minute. So let's now go back to the presentation, and I'll talk a little more about why this happens. So we have some serious polarization changes in a system that doesn't intend to do anything to polarization. Why? Well, that's because every specular surface, every transmissive optical or reflective optical surface has polarization properties. And I don't want anyone to feel insulted like, well, I knew that already. It's not that we don't know this. And if you don't know that, that's fine. But you'll be learning a little bit here. At small angles of incidence, that's what AOI means here. Small angles of incidence, polarization effects are very small. But the S polarization, the P polarization, and the average of the two are plotted here as a function of angle of incidence. And as you see, it starts to split at 10 or 15 degrees. We start to see a difference. If the angle of incidence at the surface goes to 30 or 40 degrees, it becomes pretty significant and actually, in a sense, reaches its maximum relative significance for reflection out around, in this case, for bare glass with an index of 1.5, out around 55 or 60 degrees. The P polarization reflectance goes to 0. That's Brewster's angle. It's a natural phenomenon, and it happens with glass or dielectric surfaces. Looking at bare silver, a high reflector, it's even more dramatic in some sense because the S polarization actually gets a little better, and the P polarization gets worse. So for bare silver, it's even more dramatic than it is for, in a sense, for a bare glass interface. But it's something that is really worth paying attention to. Now, I told you in the previous slide about reflectance, but this also happens in transmission. So still the bare glass reflectance, but the bare glass transmittance is complementary to this because we're assuming a lossless dielectric or dielectric interface. So they have to be complementary. So you see that also transmittance has an effect that mirrors this effect, and the S and P polarization split significantly. And so that means that we get a difference in the two components going through a system when we hit a surface. So in the Amichi singlet system, most of the polarization issues are occurring by reflection in the prism. The variation in transmission is not so significant in this because hitting all the transmitting surfaces, we're at fairly small angles of incidence. At the input and output face, essentially we're at 0 angle of incidence. At the lens, it's not a very strong lens with strong curvature, so it also has very small angle of incidence characteristic. But a variation in transmission with polarization can be really critical in fast systems. By that I mean, for instance, high NA microscope objectives, very, very fast photolithography objectives, which is one of the key frontiers of challenge for this parasitic polarization science. In photographic objectives that are very fast, or simply that have extremely deep curvatures, like extremely wide angle lenses, for example. And in fast telescopic objectives, though you see this less often than reflective problems because so many telescopes are reflective designs, at least for the fast parts of the system, for the primary in particular. So we can take that transmittance or characteristic, think about the fact that the S and P polarization components split in terms of their transmittance. One is stronger than the other. And we can actually probe a spherical surface. In this case, it's a 20 millimeter radius of curvature optic. From 0 to some very high field height. This field height here is 99% of the full radius of the surface. We very seldom do that, but in a real system, but I wanted to get this plot. So you see the angle of incidence as a function of height is very nearly linear until you get up to something like 80% of the full field height. So just something to keep in mind. It's sort of linear up to a fairly large field height and angle of incidence, but still it varies. And so if we were just putting a collimated beam through a lens based on this surface, we see some pretty significant changes in the angle of incidence as we walk up the surface. And if we then think about that through the lens, pardon the pun, if it even is one, of angle of incidence to transmittance, the transmittance of the P relative to S is going to drop as we go down. So if we had 45-degree linear polarization, the effect would be that the S component is dominating, and we actually walk, even if there's no retardance between the two, even if we just have the attenuation in transmittance between S and P, we're going to walk the linear polarization around from towards the S component direction, basically towards the lateral direction. And so it would walk linear polarization around even if there were no retardance at the surface. And that's just the way the physics works, and it makes it interesting. Now, that was a collimated source on a deeply spherical surface. Let's consider a spherical surface that is more like a typical lens with a single off-axis field source point. So I'm showing the point of the point source here. This is just showing the actual rays illuminating. And then what I do is at each point where a ray hits the surface, I calculate the angle of incidence. And then I plot the angle of incidence vector where the longest vectors are the largest angle of incidence and the shortest vectors are the smallest angle of incidence. And if we think of this through the transmittance interpretation, it means that we're going to have more of this difference between S and P transmittance over here than we do over here, for example. And it's going to show up as a change in polarization across the field. So those are all things that we just want to think about when we're designing, even if we don't calculate every angle of incidence. Since conventional aberrations depend on angle of incidence, these polarization effects do as well. So now let's talk about a few other examples of really simple systems. Coming back to reflection, the reflection of a fold mirror in an F2 beam. We're going in with 45-degree linear polarization, looking at the way the polarization effects occur, and looking at some different mirror constructions to see how they differ. These effects are a little bit subtle at F2, so you really do need to pay attention. It's enough to cause PSF problems downstream, but not enough that everybody immediately sees the subtle differences. So first, a bare silver first surface mirror going in with 45-degree linear polarization and coming out with elliptical states that vary as we go from effectively the bottom of the field to the top coming out. Well, bottom top is all relative, but from one side of the field to the other, from the side of the field that had the lowest angle of incidence to the highest angle of incidence, we see a significant effect. If we actually measured the ellipticities, which we could do in ASAP using a command like list ellipse, then we would see pretty dramatic differences here. Very low ellipticities here, much higher here. If we look at bare aluminum first surface mirror, well, we're closer to the ideal linear polarization here. We're certainly elliptical here, but it's not as dramatic a change in a sense as it is for silver. And it is kind of nice that the aluminum starts at the bottom here more or less very close to linear for a lot of purposes, probably for most imaging purposes. Now, if we protect an aluminum first surface mirror with magnesium fluoride quarter wave, then we see something that looks a lot like the protected or like the unprotected bare first surface aluminum at the bottom, looks a little worse at the top. And this is kind of intuitive. The more layers we get involved, the more likely something bad happens, unless we carefully design those layers to mitigate that, which is something that we could do and brings in the whole realm of polarization coating design. So now let's look at aluminum in three configurations. Two you've already seen. So the bare aluminum, the protected aluminum, and now bare aluminum second surface. So we're going through the glass to the aluminum, getting the aluminum from the glass side instead of the air side. And this looks really stunning. It looks great, and it might suggest to you that we would use aluminum second surface mirrors everywhere that we ever want to use a mirror, at least in the realm of the spectrum I'm in here. But there's an asterisk here for a reason. This looks great, but it is actually an oversimplified case. The case, to make it completely true, I would need to change one setting in ASAP. I turned off the front surface glass reflection, which would interfere with the back surface aluminum glass interface reflection and make things a little different. But that involves the change of one sign on one coating invocation. For those of you who know ASAP, you'll know what I'm talking about. So it's very easy to change that to make it a little more realistic, but I actually wanted to show you this dramatic result. So now let's talk about another simple system. This is a reflective system with two reflections. It's a Poro prism, a single Poro prism. And basically what we do is we go in, bounce once. We actually are going through a focus in this case, which is usually not a very good idea inside a Poro prism, and then bouncing again and coming out. Now you notice this is an uncoated Poro prism. This is an aluminum coated Poro prism. So the two reflective surfaces are metallized with aluminum in the right case over here. So in the uncoated case, a couple of things happen. One is that some gross things happen due to the fact that we are not within or not outside the critical angle for some parts of the beam. So we don't get very much energy out. Remember, the size of the polarization lines or ellipses is proportional to energy here. So in this case, the energy is incredibly low for the beams at the top and the beams at the bottom. Why is that? Because the ones on one side come out on the first interface. The ones on the other side come out at the second interface. They actually come out the back. So the top ones come out at the first interface, and then the other side of the beam is attacked at the second interface. And we lose that energy. So polarization things are happening. Clearly, we're going from linear to elliptical as we go from on axis to off, but we're also losing energy. So it's double trouble. And another thing that is worth describing here for the uncoated case, notice that the polarization ellipses for red, green, and blue, and those are actually three different wavelengths I'm tracing, are different. And why is that? Well, it's because the index for blue is higher, meaning that the critical angle is a little smaller so that I can stay outside the critical angle more easily in the blue than I can in the red. And so as the index decreases going from blue to red, the ability to get throughput at off-axis angles it worsens somewhat. I'll note that going to the coded version, we're going in with this circular polarization, and we're coming out elliptical. Whereas with the uncoded, we go in circular and even on axis to the device, not to the to these places. We see a conversion from circular to essentially linear. Okay. Had a momentary problem, but I think it's okay now. Okay, so that's the Poro prism, and let's take a look at the actual patterns. And by the way, this is something that you have to pay attention to in systems where we, for instance, change the optical axis by having a prism or something in the way. If you don't remember to look at the pattern in the right place, you can get confusing results. So when I do a plot of the output polarization, if I don't remember to turn off the leaked rays, then I get that garbage superimposed on the actual output polarization. By turning those off and only looking at the output face, I get this result. And so this is just the first time I plotted this. Though I've been using ASAP for a decade or more, I didn't know why things were weird, and that was the solution. And here, just for a clean shot, is the output of the nicely coded prism. So I'm going to go to the upshot after I clear a few things. I'm just going to turn a few things off, run at least one more thing. I want to show you that in this bare glass plot, and I'm just going to run it, get you the plot, and then show that if you get this project and want to actually get the same results as me, you'll want to use my chart template for polarization reflectance. And I ship that with this project. Just having it in the project doesn't make it work. These have to go in a specific place. And I tell you how to find that place in the little chart templates README. It's basically in the app data for whatever version of ASAP you're running. So just remember that if you actually want to run this and get the result. But that shows the same plot that I put in the presentation. Let's see. There was one other thing I wanted to show you. Let's just look at the uncoded Poro prism for a minute, because I think seeing it in 3D is helpful. So you can see what is happening here pretty clearly, I think, when you see it in 3D. And it's the same stuff that was in the presentation, but somehow a live look at it is a little more interesting. And you might really care about the polarization of the leaked rays. If you're putting this in an analytical instrument where that becomes some stray light in another part of the instrument, that could be pretty useful to you. And finally, before I get to my summary, I just want to show you an example that I really like that is a real optic that has a polarization effect that I think you might be interested in. So this is a very fast Cassegrain telescope, f.16 primary, f1 for the full system. And this is the non-polarized PSF, which looks pretty good. But the polarization PSF, this, you may say, gee, that looks the same, but there's a little bit of weirdness in the middle. The ring doesn't have the same width everywhere, the first dark ring. So if I turn on enhance, you actually see this whole thing has been squeezed a little bit by the polarization. And if I show you the polarization there, you might get a hint as to why that's true. You see a definite bias for this 45-degree input polarization. It's very nearly 45 degrees along this diagonal. and along this diagonal. But of course, the polarization is orthogonal between the two. So the interference you get in this direction is very different than in this direction. The S interference here looks more like the classical Airy. The P interference across this diagonal wipes that out to some extent because it is such a high NA. They don't overlap perfectly, and you get a reduction of visibility of that fringe. So that's it for practical systems. And one of the things I really want you to think about is, what if we cut off, we only took one quadrant of that Cassegrain and made it an off-axis system? That's typical of many big telescopes. Then things get even worse. It's crazy. And that's something that you want to be conscious of in design. So now I'll go back to the presentation and we'll finish up. So we can model these unexpected and possibly undesirable polarization effects in ASAP. Faster beams tend to excite the issues more, as they do regular aberrations. The issues are driven by the angle of incidence effects on components, and not just classical polarization components, but as I said, all components are polarization components to some extent, and at high enough angle of incidence, very dramatic. So this works in reflection or transmission for typical optical glass plastic surfaces, as well as for reflective coatings that may have a pretty complex dependence because of the complex index. And this is not just a curiosity. It is not just for geeks who look at polarization states going in and out. It affects imaging, and we saw that in the form of the PSF. This session intended to just introduce a little bit of how we look at that and evaluate it. And some of the things we might do to mitigate might include just keeping the angles of incidence as low as possible at optical surfaces, for example. But sometimes that's not possible. A fold mirror folds 45 degrees. There's not that much you can do about that. In that case, coatings and having mirrors buck each other's effects, for instance, might be useful. I hope that in examining a lot of material in a brief time, you found it useful and interesting, at least as an introduction. I appreciate your attention, and now I'd be very interested in any questions you might have. I know it takes a while to type a question to chat if it's a meaty question, so I'll give you a minute or so, and we will see from there. Okay, so the protected aluminum in this case, this was the simplest protection scheme possible. It was just a quarter wave of magnesium fluoride on aluminum. And I'm going to type that as well. So I'm typing the results so it'll be in the record and so that everyone can see it, even if you're having trouble hearing. So it's a quarter wave mag fluoride on aluminum. And so there are better ways, better protected coatings. That's just a simple one that most people can kind of intuitively understand. So that's why I used it. Okay, so the reason for change in PSF and polarization in the last slide. Now, if you're talking about this one, I'll assume you are. The reason, and I actually need to run this again because I killed one of the critical visual aids. So in this case, with the classical or with the polarization PSF, which I will enhance so that we can really see it, what is happening is that when these components in this diagonal, the diagonal that goes from the first to the third quadrant, it's S. Those are S polarization. Well, I think of it as S because the bisector between them would make it an S polarization. Those can fully interfere. They have perfect overlap, so they interfere just like unpolarized radiation in a sense. There is no reduction in visibility of when you interfere this ray with this ray. However, if you interfere this ray with this ray, let's see if I can think of a way to illustrate this. I probably can't in a pinch. I think the key thing is that if I interfere this ray with this ray, and this is and they're, let's just say for fun that they're at 30 degrees relative to each other. Those are not in plane vectors. Those vectors are actually approaching at an angle. Actually, I do believe I can find a way to illustrate this to you if I can get enough of the geometry out of the way. I think, if I'm lucky, that I can move this up, zoom in, really zoom in. And so, okay, I'm going to have to hide more geometry. You see, this is not a planar polarization characteristic. It has slight curvature. And so if this ray and this ray, the two diagonals that are cross diagonal, then they interfere with no reduction of visibility. This ray and its opposing ray have a slight angle. They are not collinear. Therefore, the visibility is reduced by that cosine factor for the overlap. So their visibility is somewhat reduced because they do not perfectly interfere. There's some non-interfering component to that becomes background, and that keeps this part of the ring from going all the way to null. So let's see. It would be great if I rotated this 45 degrees, but you can see this null is very close to the baseline, whereas this null is not. There's a great difference in visibility for that fringe, if you think of it as a fringe, relative to the other one. I hope that helps. Let's see. So now I have, does the analysis in ASAP work equally well for coherent sources as well? This polarization works. Virtually all polarization features in ASAP work, and everything I've shown you today works for coherent mode as well as for incoherent. So I would say, if you're doing polarization work using some of our new polarizer and retarder models, you want to be careful with polarized, because I still can't claim that we have tested every possible way they can interact. But for incoherent, everything works. For coherent, everything I've shown you today works. All conventional imaging and isotropic surface modeling works. Okay, so my next question is about just looking at the details of the INR file and how the polarization dependent reflectance versus AOI comes in for the aluminum surface. And so let me get you I will show you, let's see, I'll find aluminum. There's first surface aluminum, so should be able to show you that. So what I've done is I'm actually using data, and I don't remember. Oh, this is not aluminum. This is silver. Where's my aluminum data? Oh, right there at the top. Sorry. The big volume of silver data caught my attention. So the aluminum data is a fairly compact data set, and I'm actually using the complex index form, the real and imaginary part complex index form for aluminum, and it independently correlates and interpolates the real part and imaginary part to get a complex index. And so the polarization dependent reflectance with angle of incidence for aluminum is being so intricate. Having such features is because we have this complex part, which has the effect of giving us some retardance. So we don't just have a pure amplitude effect here, we have a phase effect as well that causes that polarization dependent reflectance to happen as it does for silver or aluminum. Does that help? Great. Fantastic. Any more? Okay. I saw something pop up a summary window. Oh, okay. It popped up so quickly that I didn't notice it scrolled. So the elliptical PSF so this is an observation. The elliptical polarized PSF from fast system could be confused with a standard PSF. But from the same system with an elliptical pupil, for some pupil vignetting, how would you identify which effect you have when you only measure and see the PSF? Well, if I could do anything I want, which in simulation we can do whatever we want, in the lab we can't necessarily. If I could do whatever I want, if there's any way for me to rotate the pupil, I can separate the effects. That's not too likely. But I may be able to manipulate, as in rotate the polarization, even in a real system where all I'm seeing is the PSF as a measurement. I can rotate the input polarization, and I should be able to select them. Effectively, what I need to do is excite the eigenmodes in different ways so that I can split the two effects apart. Now, it is possible to conspire in a way that they're hard to separate, but I think usually if we can rotate the polarization, or not just rotate but change the state of polarization, we may be able to pull that out. That's not a very crisp answer, but I've done these kinds of things, but it really is system dependent exactly what's possible. Is that helpful? If not, I'll be happy to talk with you more about it at length. So, very good questions. I appreciate it very much. Is there anything else? I didn't miss any, did I, as things were scrolling by? Okay, good. All right, well, I will say once again, thank you very much for joining us. I appreciate your time. I hope that for those of you who use ASAP that you want to go off and play with this. We'll get the project posted so you can use it. And for those of you who haven't played with ASAP, I hope this may motivate you to check it out. We are happy to talk with you about what you can do, and we can do trials and things like that to give you a chance to try it. Thank you very much, and I'll look forward to seeing you again sometime.